now good?
Okay.
Cool. Hey everyone. Some admin things. First off, you have class reps. Say hi.
I'm Jeremy. I'm a student at L01C Senior High School. I'm a volunteer firefighter and I have one kidney. Fun fact about me. If you have any questions, again, yeah, I can raise them. I can be a liaison.
Yeah, so we're going to be your voices to these old people. And so I'm Clyde. I go to Pack College and I volunteer. Oh, I played volleyball for my school every 3 years. I mean, for 3 years as a libero. And I volunteer every Sunday in Onehunga. So if you're ever there, hit me up. So my buffalo is, I don't have my driver's license, so I'm kind of a bum. But yeah, and also if you guys have Instagram, we have a group chat right now, so just let one of us know and we could add you to it. Yeah.
Nice. Excellent. Cool. Awesome. Thanks, guys. So other things going on. Assignment 1, hopefully you've all turned it in. If there's someone who has not turned it in, who has not gotten a hold of Peter I already, let me know at the break. The solutions will go live Thursday. We're delaying them for a little bit because there's 1 or 2 people who got only enrolled in the course very late, and so we're going to giving them a day or 2 to get a few last things in. Yes?
Was it due at 11:59:59 or 11:59:00?
59:59. Don't trust Canvas to work that well, though. Just I've had that betray me in the past. So, but if anything is right on the margins, just let us know. We can excuse it. Like, we are not going to disqualify your assignment if it is like marginally late. Don't worry about it. But when you become a university student, some lecturers enjoy having hard lines to teach students a lesson. So be careful of that. Other thing is assignment 2 is live and you can start it today. The first half of assignment, or half of assignment 2 will be approachable at the end of this lecture. The other half will be approachable into the next lecture. Try working on it. Again, as you probably saw with assignment 1, these are problems that are easier if approached early so you have time to talk to other people and think about ideas. If you try to do it all at the last minute, it can feel less pleasant. Cool. Okay. Any questions for me before we get started? No? All right. Let me just turn down the mic volume slightly because I feel like it's still really loud. That a little better? Cool. Okay. So what are we doing today? We are doing chapter 2 in the course book, which means we're talking about prime numbers and modular arithmetic. I'm assuming this is stuff that many of you all have seen before, but I still do want to go through the definitions because while you may have seen it before, you might not have seen it defined rigorously, so people sometimes make assumptions about this stuff. If you do find that you already know everything I'm doing, though, try to solve this puzzle. It's really fun. This is one of the problems that convinced me to become a math major. I really like it. It's quite tricky, and the solution involves actually series, if you can find a way to link it to that. So that's fun. Anyways, definition. First definition for the day is the following. If I give you integers, give them names, A and B, always give variables names. We say A divides B, or equivalently, A is a factor of B, or B is a multiple of A. Those all mean the exact same thing. If what happens, B is equal to A times K, for some other integer K. And the way we're going to denote this, so like notation, is we're going to have A large vertical line B. So if I write A large vertical line B, that means A divides B. Cool. So quick examples, just to make sure we're all in the same place, on the same page. 6 divides 36, that's true. 7 does not divide 100, so you might just put a slash through it. That's a bit of notation you could do. If A divides 1, what can you tell me about A? If A divides 1 and A is an integer, what is A?
Oh, it's any number.
1 or 0 does not divide 1. Negative 1, thank you. And then for what n is the statement n divides 0 true? When does n divide 0? When can I write n as a multiple of 0? Anything, right? Because we can write 0 is equal to n times 0 for all n, so for all n. Okay with this? Just making sure we're on the same page, have the same underlying notion of the ground concepts. This okay? Cool. So second definition, we're going to say that positive integer p is prime if it has exactly 2, sorry, let's try that again, positive integer factors. So just to give examples here, 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, 9 is not a prime, 11 is a prime, 13 is a prime. Is 1 a prime? No, 1 only has one factor, it's itself. So we don't include 1 here. Okay so far? Cool. This is a fun lecture to talk about with my kid who's into number blocks. He tells me that prime numbers are the ones that can only make 2 rectangles. The ones that lie on their side and the ones that stand up tall. I thought that was really cool. So, theorem about primes. We're not going to prove this in this class, but if you want to know how to prove it, email me. Happy to talk about it with you. Has a big fancy name because it's a big fancy result. This is the fundamental theorem of arithmetic. And does anyone know what this is? Ooh, hold that sum of 2 primes thought for a second. That's a different cool result we're going to mention in about 5 minutes. This says that any positive integer n can be written uniquely as the product of prime numbers, where this is, by uniquely, I do want to say up to the order that you're going to write them in. So if you had, let's say, 120, you could write this as 2 times 2 times 2 times 3 times 5, but you could also write this as 2 times 3 times 5 times 2 times 2. And morally speaking, those are the same thing. I'm not going to care about the ordering there. So this is something that you've worked with a lot, or you've worked with throughout your mathematical careers. This is hopefully not a new thing to you. We've been breaking numbers up into primes for quite some time. What I want to do for our first thing, we're actually going to get some meat on the bone here, is prove a result, which I think some of you will have seen and some of you won't, but this will be the first actual proof we're going to do with this stuff. So I've given you some examples. I've given you this theorem, which is really just a thing that I'm going to need in order to do any other math the rest of the day. So I won't prove this If you want to know how to prove it, let me know. It takes a surprising amount of work. But what I want to do is I want to start actually doing some proofs now. And so the first claim is fun result, classic result. There are infinitely many primes. Who's seen this before, by the way? Okay, good number of people. Okay, well, you've seen it before. How does it go? Yeah, basically, that's it. Cool. So if you want to structure this in terms of a proof, there's several ways of doing this. The way I like to do this is as follows. So take any list of primes. Whenever you're writing a proof, it really helps to give things names, but also keep things general. So how would you do this? If I wanted to describe an arbitrary list of prime numbers, how could you denote that? What's some notation you'd use? Should I say like 2, 3, 5, 7? Yeah, I should do like P1, P2. And now I'm not telling you what the primes are. And then if I want to say this is a list of primes, I should say, you know, up to Pn. So I could say it's a list of n primes. This is like the thing that whenever you see me do math, by the way, you just kind of gloss over. And yet when you write your own proofs, this is where people get straight up stuck every time. Whenever you're writing proofs, whenever you're doing mathematics, please do try to actually give names to the things you're working with. And when you're working with things in general, using things like ellipses, like using things like writing your list out to some arbitrary value n, this is the kind of notation that makes your proofs a lot easier. When you don't have this, you can't write this proof. When you do have it, this proof will be quite straightforward. I'll try to call this out when I do this in proofs in general, but these are the kind of techniques that make problem solving a lot more approachable. Good notation. So taking a list of primes, P1 up to Pn, what are we going to do with them? Well, as suggested, I want to look at the number formed by taking the product of all those primes and adding 1 to it. And we're going to make an observation about this. N divided by pi for any I. And again, this is me, I'm going to make a claim about any prime in my list. And so I say pi for any I. It's a nice way to notationally describe any prime in my list. If I take n and I divide it by pi, what's the remainder going to be? 1. Exactly right. Because this is a multiple of pi, it's multiple p1, multiple p2, multiple p3, dot, 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 plus 1. So it's always got remainder 1 on any of these primes. If you have a remainder 1 on division by pi, what can you tell me about the divisibility of n and pi? Does pi divide n? No, it's got remainder 1. But it is a positive integer. So we can factor into primes. And if you combine these two observations, it's not a multiple of any of the pi's, but it is a factor, it is something you can factor into primes. What can you tell me about the factors of n? You take n, you can factor into primes. Well, what about them? What do we know about them? I took n, I factor into primes. I can do that.
They're not on the list.
They're not on the list, exactly right. So what can we do? Well, we can add them to our list. And in total, what have we created a process for? I've got my list of primes. I created a way to make a number out of them that gives us new primes. How can you get infinitely many primes? What would you do? What's a thing you could do with this? Yeah, make it, or like repeat it, run a loop, make it recursive. If you just keep doing this process, you can get as many primes as you want. And if you can get as many primes as you want, there can't be a finite cap on the number of primes. You can just run this until you have any number of primes. Thus, there are infinitely many primes. Proof. You'll see a lot of different formulations of this proof. There are multiple different formulations of this in the course book. Check them out. They're all different ways to write the same kind of argument. I like to try to write proofs in different ways so you can see different ways of talking about mathematics. But are people okay with this? First proof of the day. Happy faces? Yeah. Yes. In general, you should say what you're trying to prove before you start trying to prove it. Like, if I don't tell you that I'm trying to show there's infinitely many primes, this argument doesn't make quite as much sense. So good structure is start with claim or theorem, then write your proof.
But also, is it okay to write the claim after to write the
Oh, to write the claim at the end as well? Yeah, sure. But I would definitely, it's good form to write it at the start so that the reader knows what you're trying to do. It's not necessarily going to be a fatal flaw in your proof, but it can be a thing that makes the proof more confusing. So I do recommend it. Good question. Yes?
For the example, and we're only using 2 here, no it's not. But if we have 3 and 7, and then you add 1, that gives you 22.
Yes.
That's still the factors that are, there's 11 and 2.
Yep.
1 and 2, so that's not fine. So, what are you?
So you're not given that n is a prime number. N factors into primes. So exactly what you said is a thing you could do. If you start this process and the only primes in the world you ever knew about were 3 and 7, then n would be 3 times 7 plus 1, 22, which is 2 times 11. And now you've learned 2 more primes. Now you have 2, 3, 7, 11. And you can take the product of those things. I do not know what this is off the top of my head. Does anyone know? 462 plus 1, so 463. And does anyone know what 463 factors into? Anyone have access to the internet? Is it prime? Okay. So that gives us a new prime, along with 2, 3, 7, 11. So this is not like a process for finding the primes in order, by the way. You're going to sort of walk through them in a fairly odd way. But as you keep doing this, you'll keep getting new primes each time. The primes will get kind of weird, but you will get them. And you can thus make a prime number list as large as you want. Cool. Good questions. Any other things before we move on? Neat. Okay. Where do we go to from here? So this is proof we were able to write. Most proofs you're going to try to write about primes are going to be hard. If you find yourself solving a mathematical problem in this class in particular, and you find yourself trying to like do something deep with primes, be a little afraid because most natural questions you're going to form about prime numbers are going to very quickly become humanity does not know the answer. So I'm just going to give you a few fun problems, I guess bonus exercises. If you solve any of these, I don't know, we'll get you a professorship and some extra credit, something like that. Conjecture means a thing that we don't know if it's true or false yet. So these are open problems in mathematics. When we say conjecture, it's that we have a belief that it's probably true, but we haven't proven it yet. No one knows. So the twin prime conjecture is a statement that there are infinitely many pairs n plus 2, where n n plus 2 are both prime. Big famous problem in number theory. Just give an example of some twin primes. 3 and 5, that's a twin prime. 5 and 7, that's a twin prime. 7 and 9, not, because 9's not prime, but 11 and 13 would be a twin prime. There are lots of pairs out there that go prime, comma, prime. Are there infinitely many? We don't know. We suspect the answer is yes. I think so. I was at UC Santa Barbara when we had Yutang Zhang come on. He proved a version of this where you place that 2 with like 70 million, and he proved there are infinitely many of at least that gap. Terence Tao and other people have been like trying to drive this down for several years. There's some good progress here. I forget where it is. I think it's like in the, you can place this 2 with like something in the 10,000s, and I think that's as far as we've proven it so far as human society. But natural question, thing you can explain to like your younger siblings. No one knows the answer. So second one is the Goldbach conjecture, which is following. If I give you an even number that's greater than or equal to 4, you can always write it the sum of 2 primes. So give me an even number, less than 100. Go. Someone say a number. 96. Cool. This should be able to be written as the sum of 2 primes. What are they? What could they be? I think 91's prime, he says. I think 91's prime. So I think it's a 91 plus 5. 91's not prime. Is 91 a multiple of 17? Is that what it is? 93 plus 3. Cool. Excellent. Wait, 93 is not prime. Ah, trolls. 17 and 79. 79 prime? Do we believe 79 is prime? I'll do an easier one. 64 is 3 plus 61. 8 is 5 plus 3. 6, 7, 29. There's often many ways to do this. Oh, nice. 6, 7. Yeah, good joke. So, again, this is a claim. It's really straightforward to write down. You can check this up to like, I forget how far we've manually checked this, but I think it's some huge value. But no one has actually proven this result. We don't know if it's true or not. So again, open problem, easy to say, hard to prove. If you know the Riemann hypothesis, I'm not going to try to write that down because the math gets real spicy, but functionally the Riemann hypothesis just says like, how dense are the primes? Where are the prime numbers? How likely is a random number to be prime if you're looking within some interval in space? In general, primes are hard to work with, but you can do things with them. We just proved there are infinitely many of them. I'm going to do another proof with you just to give you some more practice with these things, because it also leads into the modular arithmetic stuff we're about to do. And involve a related definition. A triple prime is going to be a triple n plus 2, n plus 4, where all those values are prime. So, for example, 357 is a triple prime, but 579 is not going to be a triple prime. I'm going to give you a theorem about these. Twin primes, giant open problem no one knows the answer to. Triple primes, we're going to find out exactly how many of them exist in the next 5 minutes. Because the theorem here is there's exactly one triple prime. So when I gave you this example right here, that's the only one that exists in the whole wide world. Probably infinitely many twin primes, no one knows, but triple primes, there's just that one. It sits there. We cherish it. We love it. How do you think you'd prove this?
Well, you say all different factors or that there are no spaces where they're at.
Right, so how do we do that? So, yeah.
These are 6k plus 1 and 6k minus 1.
6k plus 1, 6k minus 1 kind of thing. Related to that, yes. There's a step before either of these things. These are all good ideas. What is the first thing we should probably be writing down if we're doing a proof like this? If I want to prove this exactly one triple prime,
What a prime is?
well, you could write down what a prime is. We do know what that definition is. If I want to write a proof like this, I claim the first thing I would do is again, just to keep harping on the theme from before, I want to give it a name. If I'm going to write a proof, if I'm going to do anything involving 6Ks or, in this case, n's, if I want to be able to do anything, I need to define what the letter is. I need to be able to know what my notation is. So if you want to start a proof, and this goes especially hard if you don't know what to do, starting off your proof with, okay, well, if I want to show there's exactly one, I should take one of these things and I should try to study it to show there's exactly one value of it. So give things names. Naming things is powerful. So I'm going to take any triple prime, n plus 2, n plus 4. Can you talk about the 6K idea you had? What would you do with this?
Okay, I figured out how you would do this one though.
Okay, so how would you do this one?
So exactly one of them is divided by 3.
Ah, okay. Why is that true?
Because you have n, and then n plus 2 is 2 of that, and then n plus 4 is 4.
Yeah, so the idea is you're noticing that, so if you didn't see this, by the way, the next thing you do right here, you start trying to look at examples. Because this one fails because, as you said, one of them is a multiple of 3. We could try the next sort of triple you do, 7, 9, 11. That one's a multiple of 3. 9, 11, 13, multiple of 3. 11, 13, 15. Oops, sorry. That one's a multiple of 3. 13's good. Sorry, 13. 13, 15, 17. You can see in every single triple we write down, you can keep writing down a bunch of random ones starting somewhere. You'll always find one's a multiple of 3. So if you don't see the thing you've just noticed, if you just do a bunch of examples by hand, you'll quickly spot what's going on there. But once you've got that, if you want to show something as a multiple of 3, if we care about multiples of 3, we probably care about divisibility by 3. We care about how that works. So let's look at n divided by 3. And I claim to you that there are 3 possibilities here. It could have remainder 0, 1, or 2, right? We know we care about multiples of 3, so if nothing else, we did some examples by hand to notice that multiples of 3 keep coming up. So if we care about multiples of 3, we care about division by 3, we might as well look at what happens when we divide it by 3. We should see what happens. Numbers have remainder 0, 1, or 2. If you have remainder 0, well, n is multiple of 3 implies n is non-prime, or there's one other possibility, it's 3. There are primes that are multiples of 3. There's exactly one, it's 3. Cool. So if n has remainder, n of 3 has remainder 1, then n is multiple of 3 plus 1, right? That's what remainder 1 means. And if you're a multiple of 3, we should just write write that multiple as k. Again, give things names. Giving things names is very important. And if n is 3k plus 1, what is going to be a multiple of 3? Because we're trying to show that we're going to have issues with this. n plus 2 is going to be 3k plus 3, which is going to be a multiple of 3, implies n plus 2 is 3, or non-prime. When you have proofs that have different cases, this sort of column-like structure is often a fairly natural way to write down your argument. It's a way to sort of deal with all of your arguments in parallel, because often you'll see that the logic you're employing is fairly similar, so it helps you make an argument. So for 2, n is multiple of 3 plus 2, so n is equal to 3k plus 2. If n is 3k plus 2, what can you tell me is going to be a multiple of 3 that we care about in this triple? N plus 4. Exactly right. 3k plus 6. So multiple of 3, which means n plus 4 is 3, or non-prime. So if we have a triple prime, we can eliminate cases, right? We can decide those non-prime cases aren't valid, and so we can go through the cases. So either, in this case, our triple is going to be 3, 5, 7, because n is 3. In this case, n plus 2 is 3. So what is my triple here? 1, 3, 5. And is that a legitimate triple prime? No. Because 1's not a prime. And in this case, n plus 4 is my 3. So what's my triple here? Minus 1, 1, 3. And again, not legit. Yep, thank you. Okay. These contain non-primes. This is like the only solution. As claimed. Box. Yay. How are people feeling with this? Happy, sad? Yes. Thank you. Yeah. Cool. So this is how you can do proofs with primes. We're doing things with divisibility in particular. This is going to lead us into our next concept, which is modular arithmetic. Because this idea of seeing what something is on division by 3 was really useful. And it comes up a lot. And so that is going to be the next definition, and the last of the definitions that we've really got for the day. Everything else from here is going to be playing around with these definitions. So, definition. A mod B, or A, percentage symbol B, is going to be the remainder of the fraction A over B. There is a different way of talking about this that's like pretty similar but not quite the exact same. if I say that A, and I write 3 equal signs, or 3 lines like this, like an equal sign with an extra step on it, is K mod B. That's the same thing as saying A minus K is a multiple of B. It's also the same thing as saying A divided by B has remainder K, except that K can actually be plus or minus a bunch of multiples of B itself. So, yeah. Mod is short for modulo. And the operation we're defining right here is the, oh god, that handwriting was no good. This is short for modulo, which comes from modular arithmetic. Which is the precise idea of exactly what we're doing here. We're going to do arithmetic working with things up to their remainders on division. The triple line is just sort of like part of this entire statement. We pronounce that as congruent. So there's a lot of symbols here. Congruency or equivalence is another word for this. Our way of saying that these two things are the same up to multiples of B. If I say A minus K is a multiple of B, then A and K are the same up to a multiple of B. So it's kind of like 5 o'clock and 17 o'clock are the same thing up to a multiple of 12, because they're both 5, 1s, and PM. So to do some examples, make sure we're on the same page with the stuff. 21 mod 7 is what? 0. Because if I take 21 divided by 7, I have no remainder. 18 mod 5 is what? 3. Cool. 17 mod 12 is 5, exactly right. A very useful operation. What is 91 mod 2? 1. If I take any number mod 2, what's the answer always going to be? 1 or 0. What numbers are 0? Evens. And the 1s are going to be the odds. If I take any number and I look at it mod 1, what am I going to get every time? 0. If I divide anything by 1, I don't have remainders. Cool. And then to do some practice with this notation as well, if I've got 31 and I'm looking at it mod 2, what's something that has the same remainder as 31 modulo 2? Any odd number. So you might think 1, and that's true, so that would be if I did this with that, but you could also do 11. They're both the same. 31 minus 11 is going to be 20, multiple of 2. If I made this 111, 31 minus 111 is going to be 80, it's still multiple of 2. You can put a lot of things here. The important thing is that their difference will be a multiple of B. There are many things you can write here. Suppose I had 17 congruent to something, mod 10. What's congruent to 17 mod 10? So 7, because 17 minus 7 is 10. What's something else I could put here? 27. 17 minus 27 is negative 10. That's legit. This okay?
What would you use congruent as opposed to equivalent?
I think congruent and equivalent are functionally synonyms in almost every context you're going to be dealing with. Congruency is more of a geometric word, whereas equivalence is more of an algebraic word. When using equivalence, you're often talking about equivalence classes, which is something we'll get to in a future course. Actually, so I just realized what class I'm teaching. Or if you want to get to it sooner, send me an email. I can send you references. They're 99% of the time just going to be synonyms. And I can't think of a situation in which you could say one word and a mathematician would expect you to have said the other. They're functionally going to be the same. Cool. So what I want to do here before we go to the lab is to show you how to do this in MATLAB, and then write one quick MATLAB program. We're going to the lab. Any questions before I start that? Cool. Okay, so over to MATLAB, MATLAB time. So if you do like 5 percentage symbol 3, does that do what we expect? Is that 5 mod 3? No, because in MATLAB, what does the percentage symbol do? It's a comment. So this is quite tricky because it gave you an answer. So this is not a thing that's going to give you an error. You're like 5 mod 3, 5. Oh wow, this is so nice. 1,000 mod 17. It just always gives you the number on the left. Isn't that cool? Danger, danger, dangerous. This is not the syntax you do for modular arithmetic in MATLAB. It won't give you an error. It will just give you the wrong response very confidently. The notation you have for this in MATLAB is mod AB. So if you have mod 1710, this will be the remainder of 17 over 10. Give you the last digit, 7. Yeah.
What happens
If B is bigger than A, oh, that's a good question. If I have A over B where B is bigger than A, what's the remainder? Yeah. So so we had like mod, and then you just get the number on the left. So A over B, where B is bigger than A, just always gives you A back out. It's quite clean. That's a useful property. So with this in mind, I want to define a function and it's going to be a function that takes a number n and please word wrap. Why are you not word wrapping? Comments. Why is that? Okay, I killed wrap comments. It's not. There we go. So it's going to take a number n and returns true or false if n is prime or not. Cursed. Okay. Does this make sense as a function you want to write? So this is a function that hopefully should be like, I can put in 17, I'm going to get true. I should be able to put in 9, I should be able to get false. Make sense? How would you do this? If I gave you a number, how are you going to test if it's prime? What do I do? Exactly right. So what we can do is just go through all the numbers. Can I go through all the numbers? How many numbers do I have to check? Yeah, 1 up to n. Oh, I heard 1 up to square root of n. Hold that thought. You're entirely correct. But naively, you'd want to go through all the numbers up to n minus 1. Do I want to start at 1, actually? Do I want to see if 1's a multiple of, or if n's a multiple of 1? No. Yeah, I only care about primes. I have to start at 2. Cool. So a thing I do when I'm writing code is I just write comments to myself. There's like probably better stylistic ways to do this, but comments are a note that you can write down to plan out what you're about to do in your code. Later on, you can maybe clean them up, get rid of some of the other ones, but it is a good thing to do to try to offload some of the things from your brain onto the paper so that you can actually think. If you try to hold all your ideas and write all the code at the same time in your head, it's easy to get lost. Whenever you can write things down, do so. It helps. So, how do I do this? How would I write this in code? I wrote 4 here suggestively. How how do I go through all the numbers and see if they divide n? What should I write?
Just start sum equals 2 as before. Sum is
Or I can do, so I can like do d is 2 up to
n minus 1.
n minus 1. So you can make for loops start not at 1. You can start them wherever you want. D is going to be my thing I'm going to test for divisibility. And now, how am I going to do the mod thing? So I should do like mod of n and d. And what am I supposed to do about this? Yeah. So we're using like an if statement here. So there's a thing you do in MATLAB. If you want to only do something in certain situations, you can use if and else statements. What this does right here, this will do whatever I put here if this condition holds. And if it doesn't hold, it's going to do whatever I do down here. When I'm doing this, very important thing, cause of I think most typos people have when doing if-else statements, I need two equal signs here. If I just have a single equal sign, this will either generate an error or it will just always return true depending on the programming language you're working with, because a single equal sign says make the thing on the left equal to the thing on the right. And that's not a thing where you're checking if they're equal, it says make them equal. Two equal signs says see if they're equal, investigate it, see what happens. So I'm going to go through all the numbers from 2 up to n minus 1. I'm going to see if mod nd is 0. So I'm going to see if d is a divisor of n. And what should I do if d is a divisor of n? Yeah, so, and the way we return things in MATLAB is we store them in the variable. So I would say ans equals false. And what do I do otherwise?
You put it in a string, wouldn't you?
It depends on what you're doing. You can return this as a Boolean value. So you don't like have to return text. You can just return false or true. MATLAB will treat this as logical values. This is a fine and good thing to do, honestly. Trying to remember which of 0 and 1 is true or false is a good way to get them mixed up. Writing false or true is more readable code. Up to your takes, though. Do I do anything in the other case? What do I do in the other case? Okay, that's the thing we could try. I hear some suspicion, but hold that thought. Cool. So I've got this function. It's got code. What happens when I'm going to hit run, by the way? It's going to give me an error because I didn't give enough arguments. Because when you hit run, that just tries to run this function, and I haven't told it input yet. So I can't run it by hitting the run button. I go down to the command line, which I'm doing right here, and I'll plug in a number. 11. 11 is logical 1. True is 1. So 11 is prime. Was that correct? So how about prime test? What's another number we could try? 10? 10's prime. Coding's great. Is 1 a prime? What happens when I do prime test 1? Yeah, so we don't even check for 1. So there's like several flaws in here. 11 is prime, that's good. 10 is prime, that's bad. 1 is prime, that's also bad. Let's fix these one by one. Why is 10 returning a prime? Why is 10 coming up with true as the answer?
Oh, because you're not saying for all integers.
Well, I'm going through all the integers. I'm going through 2, 3, 4, 5. In the case of 10, I go through 2, which is a multiple of, so ans is false. Then I look at 3. Does 3 divide 10?
Well, yeah. So 3.3 the last case.
So does 3 evenly divide into 10? No. So you won't get a round of 0 here. So then you make it true. Does 4 divide 10 evenly? No. So the answer is still true. Does 5 divide 10? Yes, the answer is false. Does 6 divide 10? No, the answer is true. You keep flipping back and forth between false and true, but is that actually how you test primes? Do you want to switch every time you see something new? No. The first time you see something that tells you that something is not prime, you don't need to keep testing. You can stop. And so there are two different ways you can implement this. One way is to remove the else. You don't actually need to do that. And instead, we're just going to have a default value. We're going to assume that the number is prime at the start. We're going to go through all the factors. If anything proves us wrong, we'll update our answer to false. But if nothing causes us to change our mind, then it was true, because we didn't find any counterexamples. So this is a good coding way to do this. Does anyone know something else I could do here that's a nice efficiency thing? Yes. You don't need to do this, but it's a nice thing to do. If you want your code to stop doing the for loop partway through, the break command says stop. Get out of the nearest loop you're in. So this will break you out of the first for loop that this statement finds by going backwards through your code. So this is a way of saying, as soon as I find that 3 is not, like 10 divided by 3 has remainder 1, don't go any further. This can be a nice efficiency upgrade. It means you're not checking things out to some huge value. So to illustrate that, if we don't have, so let's see if this works now. Prime number 10, that's now 0. So 10 is now returning the right value. 11 is still returning the right value. So some good progress here. More zeros, come on. This is supposed to be slower. Why is this not actually doing the full loop? Okay, so we got some lag in there, right? It took some time to actually do that calculation. Why is this going so cursed? No. I think this is MATLAB doing a weird pre-cache thing where it's actually storing a set of values. Okay, so it's like taking quite a while for this thing now, right? I've added enough zeros where now it's actually computationally quite difficult to do this check. It's like taking a few seconds before you get the logical 0, right? But if we had that break statement in there, it's instant now. Except it's not, because it's crying about something else. Why are you doing this to me? So MATLAB is slightly cursed, but I claim this is actually considerably faster. Sometimes when you have a sufficiently advanced programming language, what will happen when you compile programs, it'll do optimization behind the hood to try to fix things that you should have been fixing. So efficiency gains are sometimes not obvious to see, but intuitively this break thing means we only have to go up to 2 or we have to go up to 3 before we have to stop, and that's a lot better than going up to that many zeros in the number. There's one other efficiency thing that I want to mention before we go to the labs. And someone told me I didn't have to go up to n minus 1. How far do I actually have to go up to check? Square root of n is exactly right. Why is that true? Yeah, because if I'm looking at n, some number, and I'm trying to factor it, once I go up to the square root of n, so for like 100, if I go all the way up to 10, if I'm looking at any number bigger than 10, so 11, 12, 13, what do I know about the other thing I'd have to multiply it by to get to that 100? If I'm looking at 11, 12, 13, and multiplying by something to get to 100, what are those other numbers going to have to be? Smaller than the square root, because square root times square root is the number. So I have something bigger than the square root. I have to multiply by something smaller than the square root to get the value. So if I want to get this, I just need to go up to square root of n. Square root of n is not an integer, so there's an operation called, floor, and that will let us go up to this, so that we're going up to an integer itself, so we're rounding things appropriately. Is this code complete yet? What's the one case we still haven't fixed? 1. So what should we do for 1? Because right now, we don't have a good case for that. What's a good hacky solution for this? Yeah. Now, you can just do that. This is legit. Not everything needs to be super slick. Just hard code in the fact that 1 is not a prime number. You can do that. It's fine. It's okay. Yes?
In the event of like where n is 2, would it also run an error?
For n is 2, this should be, maybe you're right. I'll do ceiling square root n. That will ensure that for n is 2, I go from 2 to 2, and I shouldn't have a headache there. In general, are there more edge cases we haven't covered here? What happens when n is 0? I'm not going to have a response, right? What happens when n is like a string of numbers? N is a negative number, n is pi. There's always more behavior to check in code. There's always a bunch of things to not check out. When you're working on a problem, we're going to try to specify exactly what your inputs and outputs are going to be. In real life, you're going to have to talk to users, and you will cry, but then you'll also be able to figure out what your inputs are going to be. There is very rarely a perfect program. There's simply steps along the path to a program that does what you want. This is now a better approach. It should give you the right answer for all positive integers. So we've made good progress. Any questions before we go to labs? People happy? Cool. Okay. Pack up, get to the labs. We'll start there at 35, because right now it's 5:25, so we'll just start there at 5:35. Cool. Talk to me if you have questions also. Yeah. Kind of vague, but does that make sense a little bit?
Yeah.
Cool. No problem. Okay. Yes. Numbat. It's a numbat. No, the numbat cannot fly. It is an Australian mammal, and I think it's one of the non-poisonous ones. So it's the default background on Ubuntu because their current release is. They always do like some alliterative thing, and it's something numbat, and I forget what thing starts with N. Numbats are cute. Okay. There we go. Okay. Oh. Cool. Okay. Let's get started with second half of class. Excellent. Thanks so much for your patience in the lab. Sorry about the technical difficulties. I'll get that sorted for future weeks so that won't reoccur, but I'm really glad that we actually got through as much of that as we did. That was really neat. What we're doing for the second half of today is building off of problem 2. So if you got there and you're like, how do you do this? That's what we're about to do. So it's a nice preview, way to motivate what we're doing in class. But to really motivate it, I want to show you that you don't need MATLAB at all. You just need your brain. Give me a very long integer, lots of digits. Go. Yeah, don't do 8, 9, 10. That'll make this way lamer as a trick. Give me something else to put up here. 4, 6, 3, 1, 7, 9. More things, more digits. 2, one more. 0. Cool. The last digit of this number is, does anyone know off the top of their head? It's 1. This last digit is 1. Give me another number, something else. Give me another number. Try to make it meaner than this one. I claim 9 made this pretty easy. 2, 2, 2, 2, 2, 2, 2. 2 the 5, 5, 5, 5, 5, 5, 5, 5, 5, 5. Okay. Last digit is, what is the last digit of this one? I think it's 8, if I haven't messed this up. But we'll see. So let me see if we did get these calculations right. So quickly over to our Deus Ex Machina. Before there were LLMs, there was Wolfram Alpha. So if you take, this is our first example here, and the last digit is indeed 1. An interesting thing to note is this is some staggeringly huge number, but we're able to find out the last digits of this pretty quickly. Wolfram Alpha is not working very hard to calculate this. And if we do 2, 2, 2, 2, 2, 2 to the effect 5, 5, 5, 5, some number 2s and 5s, it is an 8, yes, validation. We found this as well. I claim this is something that you can learn to do yourself fairly quickly using the modular arithmetic we've been practicing in this class and just be able to do in front of other people. And I don't know if it'll impress them because people are like, good math trick, nerd. But like, I think it's cool. And other math people will also possibly think it's cool. I did not go to very many parties, to be honest. I'm not good at parties. Don't look at me as an example of how to do that part of your life. Unless you want the non-example, in which case, hey. Anyways, I want to talk to you about, not about parties, I want to talk to you about how to do this and how we're able to do this pretty quickly. So how to do this? The main idea is that we have modular arithmetic, and there's a very cool thing that happens with normal arithmetic and mods, which is they play nicely with each other. You can do arithmetic mod n, and everything will work just the same as in normal arithmetic. What I mean by that is, if, as your setup, you know that a mod n is equal to b mod n, so have the same remainder, and c mod n is equal to d mod n, then if you have a plus c mod n, what's that going to be the same thing as? B plus d, because a and b are the same thing mod n, c and d are the same thing mod n. So I can just swap out a and c for what they are mod n. And I can do the same thing for multiplication. Oh, sorry, bd, thank you. And I can also do the same thing with exponentiation. A to the k mod n is equal to b to the k mod n any k. We don't have time to prove all these statements, but I can prove one of them for you. Which one would you like to see? A to the k. Everyone always wants the exponentiation. So I'm going to cheat when I do this, because if you're giving me this one to prove, I'm going to use the other ones to do it, because you use your results to do the other results. How do we do this? Well, if I want to show that a to the k mod n is converted to b to the k mod n for any k, well, I know a mod n is b mod n, which means if I do a times itself mod n, that's b times b mod n, because of this multiplication property. Just use the same thing twice. Don't use, make c and d equal to a and b. Make a equal to c, make b equal to d. And then just keep applying this, b times b mod n. And then repeat that k times. Because all exponentiation is repeated multiplication. So if I know that a times anything mod n is the same thing as b times anything mod n, if a is b and c is d mod n, then I just stack a with itself k times and get the answer. This feels like a proof where it's like, you didn't do anything. You just kind of pointed to something else you've done before, and that's how this proof works. If you know how multiplication works, you know what exponentiation is, because exponentiation is just repeated multiplication. If you'd asked me to do the proof for multiplication, I would have pointed to the addition thing, because if you know how to add things, you know how to multiply them. Multiplication is repeated addition. And if you want to do the addition one is pretty straightforward. If you just sort of write out the definitions of what modular arithmetic is, it all falls out. These kind of proofs often feel fairly unsatisfactory. That's also the other reason I don't want to do too much with them. If you don't care too much about them, I mean, check them out in the course book. That's worth looking at. But the main thing I care about is that you believe this. You can do arithmetic mod n. If you know what A and C are mod n, you can swap out A and C for their values reduced mod n, and the math all still works. People want an example of this? Feel a little vague still? Yeah, okay, I'll do a quick example of this. So what I mean by this is the following. By saying you can do arithmetic mod n, what I mean is that if you have, let's say, 71 times 13 mod 3, I don't actually have to calculate 71 and 13 mod 3. What is 71 mod 3? It's 2, because it's 1 less than 72. That's a multiple of 3. And what is 13 mod 3? 1. So when I say you can do arithmetic mod 3 or arithmetic mod n, that's what I mean. You don't have to work with the big values. You can reduce them before you do the calculation. That really helps. People feeling okay with this so far? Okay, cool. So if you've got this in mind, the use of this, the first one is you want to calculate the last digit of a to the b for some values that are very large, a and b. Well, last digit is just mod 10, right? So last digit of a to the b, so a to the b mod 10 is just a mod 10 to the b mod 10. So in other words, when I raise a to the b, I don't need to keep all of a around. When I'm doing these examples over here, all of these digits don't matter, because when I'm raising it and trying to find the last digit, I don't care about any of this. This doesn't affect the last digit. They're all multiples of 10. Similarly, these values over here don't matter. I'm reducing this modulo 10. This okay so far? So we've taken these problems, and we've just sort of simplified them by a lot, but I'm still trying to find 9 to huge value or 2 to huge value. And so the question is, how do you deal with that? And the observation here is to look at how powers behave modulo 10. So I'll do some simple examples here. If you've got 1 and you square it, you get 1 times 1, which is 1. And I multiply another 1, what do I get? I get 1 times 1 times 1 is 1. I claim if I look at powers of 1, it's always going to be 1, right? Very simple. Let's suppose that I was looking at 9. I complained that you gave me an easy one for this first example here with the 9. What's 9 squared? 81. If you apply the mod 10, you just get 1. What happens when I multiply this by 9? What do I get? Yeah, you could have 729, or you could just say, like, it's 1 times 9. I go back to 9. Multiply by 9 again, you get to 81, so 1. Multiply that, you get back to 9. You have a sort of a loop here. So odd powers of 9 have last digit 9. Even powers of 9 have last digit 1. Right? Let's try another value. So we've done 1, let's try 3. You have 3, you square 3, you get 9. What happens when you multiply by another 3? What do you get? 27. So just seven. What happens when you multiply by another 3? What do you get? 81, or just 3 times 7, 21. In either case, same last digit, 1. What happens when you multiply by 3 again? Where do you go? Back to 3. Got a loop. So you've got 1, 9, 3. Take 2 minutes, talk to people next to you, find the other things. I've done 3 digits. There are 10 in total. Find some other digits. Find some loops. In a few minutes, I want you to tell me what those loops are. Yeah. From 27 to 1? So 27 times 3 is 81. Last digit is 1. Or if you want 7 times 3 is 21, again, last digit 1. Okay. What are some other loops? This is 1, 9, and 3. What's another pattern that you know?
7, 49, 63, 21.
So 7, 9, 3, 1. 1s are always great to see, because you know you're going to go back to start when you see one of those. So 1, 3, 9, 7. What's another one? 2 goes to... Yeah, that's right. So 1, 9, 3, 7, 2. There's 2 easy ones we haven't written down yet. 5 goes to itself. 0 goes to itself. 6 goes to itself. Very nice. Sorry, I thought I could trick you. So 5, 0, 6, 1, 9, 3, 7, 2. What are we missing so far? 8 goes to 4, which goes to 4 times 8 is 2. Sorry. Yeah. Background like this. And what's the last one we got? 4, and 4 goes to, and 6. Yeah, so it goes back. So you've got in total sort of, and this will be some concepts you run into with Peter and with Johnny, because on one hand I'm drawing a graph, I've got vertices and edges connecting them. On the other hand I'm describing a dynamic system, because we have things and watching how their states evolve over time. You have 4 fixed points. This will be a term that makes sense when you talk to Peter. But it also means exactly what it looks like. They're things that stay stuck with each other. They stay stuck exactly where they are. They're not changing. You've got 2 period 2 points. So you go 9, 1, 9, 1, or 4, 6, 4, 6. And the other ones are things that have period. Oh, that's not visible at all. Haha. Still not. Oh my goodness. You won't fail me. Many.
Like right there, right?
This is a colored pencil, so I'm cheating. These are period 4 things. They've got 4 steps before they loop around, right? So this is a cool pattern. And this right here is how you can do this in a party in the back of your head. All you do is you just get rid of everything but the last digit here. If you want to know what this thing is up here, do I care about the whole number and the exponent? No, I just care about it modulo what? Yeah, I care about it either modulo 1, 2, or 4, because all I care about is the period. Because if everything repeats in 1s, 2s, or 4s, I don't have to know anything else. If I want to know 3 today's last digit, it goes 3, 9, 27, 81, 3, 9, 27, 81. It repeats in this group of 4. So if I know that I'm racing something to like the 20th, or like something followed by 20, this whole number is going to be a multiple of 4, right? I don't care about anything other than the last 2 digits, because that's all hundreds and more. Hundreds a multiple of 4. And so 20 is a multiple of 4, so this is just going to repeat in groups of 4. So even if this was a 3, I would still know exactly what it is. Kind of makes sense a little bit? So with all this in mind, I claim it's really straightforward to write a 1-line answer to your lab that we had a moment ago. So let me pull up in the lab. Shoot. Problem 2. Learner preview. If we want a quick answer to this problem in 1 line, what can we do? So d should be equal to what? Well, we know we can't do this. And the reason we know we can't do this, if you try doing mod a to the b10, what happens when I smash submit here? You get errors here. You get a bunch of things that go wrong. And why does this happen? When you calculate a to the b in MATLAB, if I have like this number right here, right? Dear MATLAB. Oh, right, scripting thing. Run the script. Yeah, it can be untitled, that's fine. Okay, so first off, if the numbers are too big, you get nan. What does nan mean? Not a number. It's too big. MATLAB sad. Okay, let's make it cry a bit less. Run. Still not. Come on. Come on. Doo-doo. Is this right? Is the last digit here 8? No, because it ends in a 0. Why is MATLAB saying 8? So MATLAB is a computer programming language, which means when it stores values, it has to put them in memory somewhere. Your computer only has a finite amount of memory. It is growing even more finite now that Sam Altman has decided to buy all the RAM in the world. Because of this, when you store variables, you cannot just have them held out to arbitrary precision. If you had numbers like the ones I was putting in the start here, the amount of space you need to write down all the digits for this kind of thing would quickly exceed the amount of storage space you could ever possibly hope to have. So MATLAB doesn't do that. Instead, when it stores values, it stores them as approximations. Typically, it's going to store them as floating point numbers. So the precision is going to be approximately 53 bits. So if your value gets any bigger than about 2 to the 50, it is going to start rounding things in ways that lead to issues like this calculation here. And so if you were approaching this problem and you wrote a to the b 10, you quickly find out that it's not able to calculate this answer correctly. Which we could see here. Like, we know that 6 to any power is supposed to be 6 for the last digit. 6 was a fixed point. But our function is turning 8. So how can we fix this? One fix we can do is don't use a, but just replace it with the last digit. That wouldn't have helped us here. A was already a single-digit number, but if a was bigger, that could have helped us. What's the simplification you can do to the power? Do we need to know the whole power? No. What is the only thing you need to know about the power? You need to know what it is mod 1, 2, or 4, right? So there's two approaches. You could try to do cases. You could look at what a mod 10 is, and then if you saw that a mod 10 was 1, you return 1. If it's 9, you look at the power mod 2 and you return 9 or 1. If it's 506, you just return 506. If it's one of these things, you look at the power mod 4 and return 3, 9, 7, 1 in cases. You can write a bunch of cases for your code. There's a simpler approach, though, which is the following. Every single one of these cycles here is a divisor of 4. So indeed, all I need to know if I'm raising 1 to any power is just the answer is going to be 1. But I could actually just like raise it to 1, 1 squared, 1 cubed, 1 to the 4th, and it's still going to stay 1. For the powers of 9, I do 9, 1, 9, 1 back and forth. But I don't have to think of this as a period 2 thing if I don't want to. I could be slightly dumb. I could be like, I could think of this as not going 9, 1, but I could think of this going 9, 1, 9, 1, back around. Any period 2 point is, in a dumb sense, a period 4 point. And so if I want to do this all in one line, I just say, I look at A's last digit, and I raise it to B mod 4. Wait, no. Why? Why are you doing this to me? I persuaded you. You thought I was telling you the truth. Why is this giving me an error now? So this is the fun part of code, by the way. I think you all believed me a second ago, and now it's red. What is happening? What is our function returning in this case? 1. Why is our function returning 1 here? Oh, yeah, thank you. Actually, no, this is a good experience. Talk to each other. Why isn't it working? It should work. We thought it would work. Why is it not working? Is there a pattern with what's going wrong every time I hit submit? It's always 1. Has anyone spotted the error, the flaw here? What is it?
Is it when returning more, the answer is 0?
Yes. So there's a thing I said in like our first lecture, which is if you ever want to sound clever in class, like say, what happens when it's 0 or things like this. 0 and small numbers are almost always going to be the weird edge cases that wind up tripping you up with code is otherwise sensible. Because what is any number to the 0? 1. And so because we're doing this trick, when the mod power is 0, we are not following our nice patterns anymore. We're just saying, nope, output 1, I'm done. And so we are doing the right pattern thing, except for when it's 0, in which case we're outputting 1 as opposed to doing our nice pattern thing we should be doing. What's a hack for this? What's a very simple fix? Yeah? Add 4. Thank you. That is exactly the thing I was hoping someone would say. Oh, no, don't say. If the issue is that 0 is causing headaches, don't start your loop at, don't do 0, 1, 2, 3. Why not just do 4, 5, 6, 7? It's a computer. It can calculate a to the 4, 5, 6, and 7. It's not going to cry. It'll be just fine. And so this is slightly less computationally efficient than other paths you could take. But it fits in one line. It's very efficient. And all you have to know is how to raise numbers between single-digit numbers to 4, 5, 6, and 7. It's something that happens very quickly. How are people feeling with this? Does this kind of make sense? I did want to go through that debugging process as well. In particular, the thing that I did in between where I just mash submit a bunch of times and try to find a pattern for what cases are giving us an issue. This is a good thing to do. If your code isn't working, try to find a pattern in the cases that it's not accepting. This is a good way to debug. People happy with this? Cool. Awesome. Okay, we've got about 13 minutes. And so what I think I want to do is do 1 or 2 quick modular arithmetic proofs just to give you some more practice how that feels. Sound good? Cool. Okay. So let's do 1 or 2 speedy mod proofs. So claim, just to give you practice with these kinds of arguments, because they're useful to be able to do, I claim to you that if I give you a number and I look at it mod 3, and it's multiple of 3, then, oh, thank you. Camera. Sorry, this is a not. There we go. I was like, wait, this is cursed. If you give me something that's not a multiple of 3, if I square it and take away 1, I do get a multiple of 3. That's my claim to you. Make sense as a mathematical claim? So if you gave me like 2, I square it and take away 1, I get 3. If you gave me 8, I square it as 64, take away 1, I get 63. How would you write a proof of this? What would you do? Yeah. If I want to write some claim about n modulo 3, I should say take any n this is not a multiple of 3. Again, when I'm starting my proofs, I need to give things names. I've been doing claim about n. I should take any n. I'm not writing down what n is. This is how we start writing these proofs. We write down claims in general, talking about what the names of the things we are and what properties they have. Next thing we do, whenever you have a definition at hand, it's good to employ it. We know that n is not a multiple of 3. if n is not a multiple of 3, then what are the possibilities for n mod 3?
1 or 2.
Yeah. N mod 3 is 1 or n mod 3 is 2. Now, the next thing you do with this, every time in modular arithmetic proofs, which is why I want to do it with you right now, if n mod 3 is 1, what does that mean about n? That means n is a multiple of 3 plus 1. And if n mod 3 is 2, then n is a multiple of 3 plus 2 for some k. This step right here is the most critical step in this entire proof. If you know how to get to the step, you are going to succeed at this proof. This is, again, give things names. And the naming thing we're doing here is saying, what does it mean to have remainder 1? Well, it means you're a multiple of 3 plus 1. And what is that multiple of 3 going to be? I'm going to give it a name. It's going to be 3k. It doesn't look like I'm doing much, but I claim that is the only hard part in this proof, is knowing how to write this line. Because if n has this form, what is n squared minus 1 going to be? That's what we care about for our claim. That'll be 3k plus 1 squared. Do algebra. 9k squared plus 6k plus 1. We have the minus 1 coming along for the ride. 9k squared plus 6k, which we can factor 3 out of, so we get 3k squared plus 2k, which is a multiple of 3. So in this case, we're done. We've proven our claim. And over here, do the same thing. This is like the algebra on autopilot step of the proof. 3k plus 2 squared minus 1. 9k squared plus 12k, because you get 2 times 3k, 2 times 3k, plus 4 minus 1, which is 9k squared plus 12k plus 3, which I'll skip the intermediate algebraic step. This is a multiple of 3, because everything here is a multiple of 3. And so in either case, we've proven our claim, and so we're done. People happy with this? This kind of makes sense? Cool. When you find yourself tackling modular arithmetic problems, this is the kind of process that I'm hoping that you'll take. You'll give your things names, you apply the definition of mods. With mods, you frequently wind up with cases. When you have these things, you say, what does it mean to be remainder 1? Well, I'm 3k plus 1. And once you've done that step, it is just algebra, proof flows downhill, everything works. It's great. Cool. This okay? Should we do one more before we run out for the day? Okay, we'll do one more. Same process. There is no n such that n squared mod 5 is equal to 3. Proof. How would you do this? What's the first line going to be? What are we going to write down here? Yeah. Take any n. What should I look at with this n? If you've got this as your problem's context, what should we be considering here? We should square it, but what do we need to do before we square it? What are we going to care about in the end? Because if we square it, just write, okay, I have n squared. We don't know what to do with it. What does the problem suggest that we investigate with n? Yeah. Look at n mod 5. You're going to get 5 cases. N is going to equal to 5k, or 5k plus 1, or 5k plus 2, or 5k plus 3, or 5k plus 4, right? because I'm just looking at what n mod 5 is. It's 0, 1, 2, 3, or 4. And if you are in any of these cases, n squared is going to be 25k. And so when I look at this, 25k squared, sorry. When I look at this mod 5, thank you for that, I'm going to get 0. When I look at 5k plus 1 squared, I'm going to get 25k squared plus 10k plus 1. Mod 5, you're going to get just the 1. If we look at 5k plus 2 squared, we're going to get terms I don't actually care about, 25k squared plus 20k. They're always going to be multiples of 5, because this 5 here is just going to be attached to all the things I'm going to get. All I care about is this last term, 4. Mod 5 is going to be 4. And when I do this one right here, the 3 term, I get 5k plus 3 squared is equal to, again, terms that are not going to matter, because they're all going to be multiples of this 5 thing here. So plus 9. And mod 5, what's the 9 going to be? 1, 4, 4. And then when I do the 5k plus 4 squared, dot, 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 skip the algebra, you're going to get 1 as well, because 4 squared is 16, mod 5 is 1. All the terms are going to have 5s attached. They're going to die when you do mod 5 stuff. So you get 0, 1, 4, 4, 1. There's a nice symmetry that's going around here. This is a thing that mathematically holds in general. There's a lot of cool things you can do with that. But none of these are 3. And so the claim is true. You cannot square a number, look at it mod 5, and get 3. It's impossible. It never happens. And we proved it. And we proved it by looking at our definition, working with cases, expanding things out, and just going on autopilot from there. Does this feel okay? A lot of proofs at the start. People have a lot of anxiety. I got a lot of questions on Ed about, like, does this count as a proof? A lot of what this class is getting used to proofs. When you get more practice with them, they do feel kind of like this. It's kind of this downhill, almost autopilot thing. You're just explaining why a thing is true. In many situations, the reason a thing is true is basically look at the definitions and go through the cases, and you're done. You just have to fill in the algebra. Happy? Happy? Yeah, okay, cool. Done. End of class.